Hey there, I'm Keenan Fry, and this is the Acid Drip. So this is the next part in my tutorial for blind and visually impaired individuals working with basic electrical. I want to start off by putting out a disclaimer. I am not an electrician, and nothing I say should be construed as advice, and I am not responsible for any of your actions whatsoever when it comes to messing with electrical. If you are unsure of your safety when working with electrical devices, contact a professional and ask them for their advice. Best practice is the safest practice. So, quick update. I went through the whole video series that I recorded last week, Friday, April 9th, I believe, and scrubbed all the footage, synced the audio, and then as I was going through everything, realized I made a small mistake in a couple of my explanations. It's because things got actually a little bit more complicated, but in a good way. I want to start off by explaining that this GFCI, that's a ground fault circuit interrupter that is connected to the backsplash of the kitchen. It's right next to the stove, and it's usually where we use our toaster. This GFCI actually is potentially damaged, which made my video on this a little bit more complicated than I had initially anticipated, because I worked in the bathroom, which you've seen already in the previous video where we look at the GFCI in the bathroom, the one that's actually more friendly to the visually impaired. It's got a black disengage test and then a red engage reset. That receptacle was working fine. The bathroom one works as it should when it is engaged in test mode, which means that the breaker that is built into the GFCI decouples, which deactivates the GFCI. That breaker works as it should. Okay, so the bathroom is fine. This one though is doing some weird stuff, and that kind of threw me off because I had to figure out what was going on in my kitchen. So it's kind of annoying because it means that something's going on with the GFCI here, and we probably have to take it out and replace it. And on the other hand, because it's broken, it gives me the perfect chance to demonstrate like what can kind of go wrong with a GFCI. So I apologize that there was kind of a delay in me publishing things, but this was kind of weird, but it's also kind of a great opportunity to explain some things to you because it is broken, and we're going to talk about how to be safe and how to detect a potentially broken outlet. We're going to talk about testing a potentially broken outlet with two tools. We're going to talk about using the voltmeter, which is in my hand. This is a older model. It's a GB Instruments voltmeter. It's a rectangular gray box. In the center it has a dial that resembles an egg timer, and on the top there is a needle dial, and the needle dial flickers back and forth depending on the reading you're getting. There's a series of very complicated measurements that are labeled on it. And really there's a lot more on this device than what most people are going to need. On the other hand, I have my Klein tool, which you probably just heard beep. I'm going to turn it off real quick. You heard it beep right there twice. This is a much more friendly tool. As you can tell by the beep, it gives you an auditory cue when it's active, deactive, and it gives you an auditory cue when it is reading a voltage. Now, this tool, the Klein tool, it's kind of like a large magic marker that's got a yellow casing and a clear plastic tip, and then a single button. It's not going to give you a reading per se. It will give you an alert, but not a specific measurement or reading. This is a tester. This Klein tool is a voltage tester. It's going to test if there is a voltage coming from a receptacle or electrical device. And this GB Instruments right here, this is a voltmeter. It will measure the amount of voltage coming out of your receptacle. And we're going to talk about the differences between the two and some ways of using this technology in an accessible manner. So let's get into it. Okay, for starters, let's work with the more difficult tool because it's going to kind of cover all of our bases and kind of give you a comprehensive explanation of how electrical works on a basic level in your home, and then we'll go into the volt tester, which is a little bit more simplified but more accessible. So this voltmeter, again, I told you, it doesn't give you any auditory cues. It's got small, tiny little print. It's not exactly the most user-friendly device, and you kind of have to know what it is you're doing with it for it to be useful. Some additional details about this voltmeter. There are two nodes, or prongs. They are two long wires that extend from the box. And at the end of the wires is kind of what looks like a toothpick, almost as if there was a toothpick with a little diamond shape on the tip. And the diamond shape is to help the prong catch inside the receptacle. So we're going to talk about how that works. For starters, I'm holding in my hand the red receptacle, or the red prong, which goes into the live receptacle, and this is the one that is going to initiate the current. It has a maximum capacity of 500 volts. We're going to talk about that in a second. And in my other hand, I have the black prong, the neutral or ground prong. And we're going to talk about this. Coming out of your wall is 120 volts. And that is AC, alternating current. Now, AC is different from DC. AC, alternating current, means that the flow of electrons is switching back and forth between the line. That's about the most I'm going to say about that because it gets really complicated really fast. DC is different. It's direct current. It's a singular flow through the circuit. So DC is battery operated. Things like flashlights, cars, your cell phone, things like that. Those are going to be DC based. Okay, so we know that the wall is AC. We have our voltmeter in our hand. Now our voltmeter, I told you, has a dial that resembles an egg timer. Now, when the voltmeter is centrally located, that means the dial is facing up 12 o'clock, it's off. But if we turn it to the left, we're going to be using the DC readings, which would be, again, for batteries and so forth. And if we turn it to the right, we're going to be using the AC readings. Since we are dealing with a home receptacle, we're going to use the AC settings. Now, the home receptacle is set at 120 volts. Now, give or take, any outlet in your home will give between 110 to 120 volts. So if it fluctuates a little bit, like it's at 118 or something like that, that's fine. It's not going to always be a perfect 120, but it should be above 110 and at 120. And if it's giving you more than 120, that's kind of odd, but that's its own thing. Looking at the AC settings on this voltmeter, we have 10 volts, 50 volts, 250, and 500. So this is a maximum capacity of 500. We need to choose the appropriate setting for measuring our wall receptacle charge, particularly the volts that are coming out of the receptacle. Now, if we use a setting like 10 and the wall is giving out 120, the wall has more volts coming out of it than what this device can tolerate, which means it's going to burn out the device. If we do it at 50, it's the same problem. However, if we do it at 250, this setting on the device will tolerate the voltage coming from the wall. Additionally, we could do it at 500. Here's why we do it at the 250 and not 500. If you use 500, you are going to be creating a circuit inside the voltmeter that has a very wide bandwidth, which means that it will have a larger margin of error when measuring lower currents. So, if you use a overwhelmingly large setting, it will undermine the accuracy of the voltmeter, and it might give you a reading that's actually way lower than what the wall is actually outputting, which could give you a false result telling you that, oh, your receptacle isn't working properly, when actually it is, and the mistake you made was that you used the wrong setting on the meter. So you want to use the setting that is one step higher than whatever voltage is coming out of your wall. Now this is relevant because when you travel to other countries, they will use different voltages in their receptacles. That's why you have those special adapters. And this is going to be useful for you because if you like to travel, this tool will protect your electrical devices. It will also protect you from getting a potential shock. So let's talk about that now. I'm going to set my device to 250 volts, and I'm going to line it up against the backsplash. I have in my hands my two nodes. In my right hand, I have my live red electrical node, and I have in my left hand the black neutral node. Now, we're going to do a little example of electrical safety. I am going to put in the black node first. Okay? This is really important. Now, if you are visually impaired, you may actually have enough vision through high contrast to be able to tell the difference between the black node and the red node. But if you don't have the means to do that, I would not recommend performing this test with this tool. I would recommend performing the test with the volt tester instead of the voltmeter, which is why I'm providing examples of both those tools so that I can try to cover the bandwidth of the audience. So, the black receptacle, or the black node goes into the neutral receptacle. The neutral receptacle is always going to be, in the United States, the left plug in the receptacle. So there is a left plug, a right plug, and a ground plug at the bottom. The left is neutral, the bottom is ground, the right is live. So as you can see from the meter, the dial is not activating, the needle is not receiving a current. And what that means is that the neutral in this is actually working the way it should. Now if I touch this, which is dubious, don't do this. I'm doing this because I've checked this thing and I figured out what's wrong with this receptacle. I'm going to touch this red receptacle, okay? I didn't get a shock. Okay, here's why. The neutral is not giving a charge and it's not backfeeding, which is good. What's going on is, if I had put instead in the opposite order the red live, and I had put that into the outlet, and I had instead touched the black lead, I would have received a shock. And that's because the live is in the proper receptacle, the right side. It's sending a current from the right side of the receptacle into the node. The node is transmitting that through the voltmeter, and then it's sending it through the other end of the voltmeter to the black node, which means the tip of the black node, that toothpick with the weird little diamond on the tip that I told you about, that is now live and will shock you. Okay, so for receptacle safety and for voltmeter safety, what you do is you do the black side in first and then the live side. Now technically, if this was backfeeding, it could have potentially shocked me. We'll talk about backfeeding later on. So here we go. I'm now inserting the red prong, the red test node, into the receptacle, and we get a reading of 120 volts, which means that this receptacle is functioning in a relatively normal fashion. Okay, so we're now going to remove the red receptacle. Inverse operations. The red receptacle is put in last, but it is removed first for safety. We are then going to remove the black one. Now it's discharged, it can't shock me, can't hurt anyone, it's safe. Okay, we're going to perform the same test with the second outlet in this same receptacle, okay? Okay, there we go, that's set up. Black node goes in first, boom, here we go. That's in, red node goes in, and we get another 120. So both of these outlets are giving the proper voltage. So there's a problem with the receptacle, but it doesn't have to do with the volt output. It has something to do with the GFCI. We're going to talk about that. The way the GFCI works is that there's 120 volts coming out of this outlet. If the GFCI is functioning properly, what will happen is you'll have something like a toaster plugged in or a hairdryer if you're in your bathroom. And I use the hairdryer example because earlier we tested the receptacle in my bathroom and we found that it worked perfectly fine. First, it deactivated as it was supposed to. It reset as it was supposed to. What's interesting about this receptacle in my kitchen, the backsplash of my kitchen, is that it's not resetting properly. So we've got a few things to talk about. We got to talk about why this receptacle is not working, what's going on with the breaker. We have to talk about different voltages and how that works internationally. And then we have to talk about backfeeding due to bootlegging. Okay, those are three kind of complicated topics, but we're going to go over them right here. And then at the end, very end, we're also going to talk about the garden hose metaphor, but that'll come later on. So what I'm going to do is I'm going to deactivate the GFCI here. Now, this GFCI is less user-friendly than the other one because it's a white plate with two white buttons. So there's no contrast, there's really no way to tell, and then there's teeny tiny little font that like even I have problems seeing, and I've got typical sight. So this thing isn't actually very good. And there's a couple of issues with GFCIs. They're technically designed to be universal, so you can install them upside down. So this GFCI is typically installed. That means the two prongs that are the right side live, the left side neutral, are top side, and then the ground is beneath them. Now, because it's a universal GFCI, it can be flipped upside down. If you flip the GFCI upside down, you also flip the order of the buttons. Well, normally, the bottom button is always the test, and the top is the reset. The test deactivates. We're going to push the test. You're going to hear an audible click. Okay, there was the click. Now, technically, this GFCI should be deactivated. It's not. There's something wrong with the breaker in here. It's not actually deactivating the way it should. And I'm still getting voltage tests readings from this thing. We're now going to reset it, though, just so you can kind of hear how that sounds. Here's the reset. Okay. You may have noticed, if you have sight, that at the bottom right corner there was a light. Now that light flashed. It started off green when it was live, telling you that there's power going through here. It turned black, which deactivated, said that the GFCI was deactivated, and then it flashed red and then turned green when we reactivated it. So it's got a test light that's telling you that it's deactive, but something's still going on in there. Now, going back to the order of the buttons, because you can install it upside down, you could technically have the test on top and the reset on bottom. The test will always deactivate the GFCI if the GFCI is functioning normally. So you have to make sure that the GFCI is installed right side up, which means the two prongs then the ground. If it's upside down, the ground will be on top, the two prongs will be on the bottom. And to make things more complicated, if you travel internationally, because the plugs are completely different in every country, there's a different series in England, there's a different series in France, Germany, Italy. So I think there's also one for Spain as well, which is really annoying because if you ever go to Europe, it's like every single country you're going to need a different adapter. And do not buy a universal adapter that transmits to all of them because they are all different voltages. You'd have to have a really big device with multiple capacitors resisting the flow of electricity to accurately compensate for a device that has a universal output for multiple countries. Those devices don't really exist. So what you'll see on the marketplace are these cheap Chinese-made devices that are not safe because the grounds aren't actually even connected to the actual ground plug. So you're sticking a device into the adapter and there's no ground connected to the actual ground prong. So like that's really dangerous. And then you've got all these little like cross wires inside of it. It's a bad, it's all bad. So what you want to do is you want to get unique adapters for every country you're visiting. Number one, always use unique adapters. Do not get universal ones that can mix and match. That's always a mistake. Next, you need to know how that adapter works. Is it upside down, right side up? And then you need to go into your hotel room, if it's an Airbnb or whatever, and check to make sure that the receptacles are actually working right. The ones that you're going to be plugging, say, your laptop, your cell phone into. And this is important because you don't want your devices to get burnt out and you don't want to get shocked. So this GFCI is installed right side up. The deactivation is at the bottom, and that's the test switch. The activation, which is the reset, is on top. It's poorly labeled because it's a white on white, so I would use 2 bump dots, and I'd probably get a Sharpie out and get a red Sharpie for the reset and a black Sharpie for the test, and I would do that. Now what's going to happen is I'm going to deactivate it one more time. There's the auditory pop. I set the voltmeter up to 120 again. Okay, there we go. I am going to insert the black prong first. Okay, here we go, black prong, and then the red one. Okay, the top one is not giving a reading. The ground, it's not giving a reading. That's good. Okay, we're going to do the same thing again. We're going to go to the neutral and then to the 5 on the bottom prong. Okay, that's good. Now we're going to go to the ground. Okay, there we go. So what's going on is something is happening with this GFCI where when I'm tweaking around the little diodes, I am getting a small reading coming in there. I don't know if it's the voltmeter giving me a weird feedback or if it is the actual receptacle. This is coming from the voltmeter. We're now going to use the Klein tool to diagnose this. The Klein tool is the tool that is going to be most accessible to a blind individual because it gives that auditory beep. So now what we're going to do is I'm going to remove the red lead. Remember, inverse operations, red goes in last, comes out first. Then we're going to remove the black lead. It's now deactivated and it's now safe. Okay, voltmeter is off. So I'm going to bust out my Klein tool. This is the volt tester. Now this is just going to detect if there's voltage going through the GFCI. And this is the part that's kind of confusing and is a little bit odd and is telling me that there's something weird going on with this outlet. So let's check this out. Okay, that first beep indicates that the Klein tool is active, and for those of you who have some light perception, you'll notice that a green light goes on. That tells you that it's active, it's on, but it's not detecting anything. Let's go ahead and start with the neutral. The GFCI is still active, deactivated, mind you. Okay, no reading, ground. Okay, beep because I pushed it a little too hard. Ground is no active. Okay, so that beep, and I just turned it off now so you hear the double beep, but that series of beeps that you heard was when I stuck the Klein tool. This is a volt tester. It's testing to see if there's any voltage. Okay? The volt tester is still going off, which is weird because from what I understand, if the GFCI is deactivated, as it is, I have not reactivated it, you haven't heard the second pop from the test being deactivated and the reset being activated. So what should be happening right now is there shouldn't be anything going through this. There shouldn't be anything. So I'm going to turn on the Klein tool and I'm going to test the GFCI again. Okay, Klein tool's on. Here we go. We're going to test now the top right receptacle. This is the top right lead. Okay, we're getting the beep again. We're going to test the bottom right receptacle. Turned it off. We were getting feeds from both of them, even though the GFCI is deactivated. And that's inconsistent with the bathroom test where nothing was activated whatsoever. The top outlet and the bottom outlet that were both the live prongs. So there's two live prongs, the right side, top and bottom, were both completely deactivated. Cannot emphasize that enough. They were both deactivated when the GFCI was in test, which means that it's deactive, the breaker has been disconnected, there is no circuit, which means that that should not be happening. I don't know what's going on. This device isn't really telling me what's wrong, but it is telling me something is wrong. That's the value of the Klein tool. It's not going to tell you, hey, you know, this is the reading and it's off. The voltmeter should be doing that. For some reason, it's not coming up on the meter, which means I need to do even more research into this and dive into it some more. It's kind of a rabbit hole. It keeps expanding and so forth. But from what I can tell by using this Klein tool volt tester, which is a really simple tool that you can take while you're traveling, and that's really important because what's coming out of the wall is 120 volts. It will vary for different countries. And if the GFCI is functioning normally, what will happen is the GFCI will detect if there's any spillage. What that means is, let's say you have a 100 watt hair dryer plugged into the bathroom, and you have 120 watts being drawn from the receptacle, or being offered by the receptacle. There's 120 being offered, and 100 is being drawn. Okay, think of it like a bank account. You have 100 being pulled out. But that 100 isn't returning back into the receptacle. Let's say instead 88 is returning. So there's like a voltage of 12, give or take, that's missing, that's not returning to the receptacle. The GFCI should detect that difference, the discrepancy, and deactivate the receptacle so you don't get that shock. That's how it's supposed to work. This will tell you if the GFCI is truly deactivated when you put it in test mode, which is what we're recognizing here, is that in test mode this shouldn't be giving any charge. It is giving a charge. The bathroom one in test mode does not give a charge. That means it's working functionally. And what that's telling us is there's something going on here. So we've kind of explained what's coming out of your wall, how it circulates through your device back into the wall, and why it's important to be able to test for discrepancies in the charge that is leaving the wall and returning, and how that can lead to a potential shock. Now, some other things about bootstrapping, because we mentioned that bootstrapping is when an electrician is brought in, usually during a remodel, to do a very quick electrical test, check to make sure the outlets work and are up to code. Usually contractors have an electrician that they're friends with on call to do these kinds of tests. Now the problem is, because the electrician is incentivized to perform the job as quickly as possible so that they can turn around the approval for the city inspector to come in and do the final inspection, because the lead electrician is incentivized to turn that around as fast as possible, oftentimes things happen like bootstrapping. So an instance of bootstrapping is that in this particular case, this GFCI should have two neutrals. They should be isolated neutrals. All neutrals in your house should be isolated. A bootstrap neutral is when two outlets share a single neutral. The problem with that is you send current from the live into the neutral, right? So if you have a top receptacle that's live, and it's the top right, and you have the top left neutral, and then in the bottom receptacle you have the bottom right and the bottom left, and the bottom lefts are tied together in your wall. That means where they feed through your wall back to the electrical panel, the electrical board, if they share a line, a tied neutral, that's called a bootstrap, then what's going to happen is electricity is going to pass, say, from the top outlet to the top neutral, completing a circuit. Let's say your toaster's plugged into the top outlet, but this bottom outlet's also going to be live, which means anything that you plug into here will probably shock you. And the reason is because the neutrals are being shared. So the electrical charge is going from the live side to the neutral side, but then the neutral side at the bottom is receiving some of that charge as well, because it's looking for the easiest path back to the board. And then as soon as you complete it and put it into continuity, you can get a shock from that. And that's backfeeding. Okay, so remember when I did the stupid thing and I touched my receptacle while the prong was in there? Okay, technically if this receptacle was backfeeding, that could have shocked me, because what would have happened is, instead of it feeding the way it normally would have, it would have given me a shock. The way that could have happened is, let's say, as I showed you earlier, the black prong is in the neutral outlet and I'm touching it. Let's say that the bottom and top are wired together. Well, if that's the case, there could be a charge coming through there that could shock me from the bottom live receptacle. It's very complicated, but everything should have an isolated circuit, and electricity will always find a way to complete its circuit by the easiest means possible, even if that means going through your body, which is very painful and should be avoided at all costs. You know, nature finds a way. Name that movie. Anyway, that's like some basic stuff about GFCIs, using a voltmeter, using the Klein tester. You can bring the Klein tester with you when you go international. The plastic tip should fit in most wall receptacles internationally. It will be able to tell you if the breaker is truly deactivated and if the outlet is safe. And then it'll also tell you if your adapter is working properly, because your adapter should actually have a built-in breaker. You should not buy an adapter that does not have its own built-in GFCI. They're a little bit more expensive. They're usually in the $10 to $15 range, but they're much safer, and they will protect your electrical devices and they will protect you. I've seen these cheap Chinese adapters that are just made in bulk, and they've got like 7 or 8 different plugs, and I'm going to link you to a YouTube video where there's a guy who bought one of those off of eBay for like $1 and he opens it up and it doesn't even have a connection to the ground, which means the thing will just, 1, shock you, and 2, start a fire, and that's just terrifying in its own right. So you can't be cheap with electrical. You have to buy the right adapters. You have to have some kind of tool with you when you're traveling, because you don't know if somebody recently renovated the room or the building and did a slap chop. Because you can bootstrap a wire and technically it'll pass code. There are ways where you can fool the inspector. And usually the only way people figure out that something is bootstrapped is when they rip the tile off the wall, or they rip the sheetrock off the wall, and they go through everything and actually look how it's all wired to the board. So that's a real problem, and you don't know when you're going on a trip if your room is actually safe, if the place has actually been set up properly. And it's kind of unfortunate, but it's on you to kind of take accountability for that and have, you know, a means of checking that and protecting your own safety. That was a really long video. I had to explain a lot of different parts. We're going to come now to the end of everything and do the wrap up, and I'm going to give you the garden hose metaphor, which will explain the difference between volts and amps and what watts are, and will help you understand how your electrical devices work and how they're rated, and then you can figure out if your device is safe to plug into the wall or if you need to, you know, figure something else out. So we'll come back in just a moment. And I appreciate your patience. I know this was a long video, but I really appreciate your patience, because there's a lot of nuance to this. So I'm Keenan Fry. I'll see you in just a moment. Thanks for watching.